Dear students, today we'll continue with our conversions. Okay. Before starting conversions, we like to discuss a few things regarding oxidation and reduction. Okay. So first, if we have a primary alcohol like this one, ethanol. Okay. So this is our primary alcohol. When you do a control oxidation, so for that we have two options: either chromium trioxide, or you can use as a PCC. We call it, it's a pyridium chlorochromate. Then it will end up with our aldehyde. Okay, so we call it, this is a controlled oxidation. Then if we go for the further oxidation, we'll have two options. That is, you can use a alkaline KMnO4 or acidic K2Cr2O7. Alright, so these are strong oxidizing agent. So if you use that, this will be end up with our carboxylic acid. Okay, so if you directly apply this reagent, that is alcoholic KMnO4 or acidic K2Cr2O7, strong oxidizing acid, to the primary alcohol, it will directly end up with the carboxylic acid. Now, but if we start with our secondary alcohol, suppose this one, right, propane to all. So this is secondary alcohol, right? This carbon has two branches, right? So if we do a control oxidation, so the same reagent, or you can use as a pyridinium chlorochromate, then it will end up with the ketone. Yes. Right. So now what will happen if we use this strong oxidizing agent in case of secondary alcohol? Then it will break. Okay, this bond, this CC or this side, this carbon, this bond will break. Okay, so if this side break, then it will form a CH3COOH plus HCOOH, forming acid. If this side is break, then again it's a CH3COOH, and this carbon will make as a HCOOH. Okay, so forming acid. So if we have two different groups in this side, okay, and either side, if we have two different group in both sides, then we'll have four different products. Okay, so that becomes useless. That reaction becomes useless because we are getting four products, right? So that is normally we do not use. So in case of primary alcohol we can use because we get a single product, but in case of secondary alcohol we may get four different carboxylic acids. Okay. Now coming back to the backwards, like what will happen if we do a strong reducing agent? So that is, we have a reducing agent as a lithium aluminum hydride, okay, or we have a sodium borohydride also, BH4. So if you use this reducing agent, it will come back to our primary alcohol. Similarly, in case of this aldehyde also, if you use the same reagent, okay, lithium aluminum hydride or sodium borohydride, this aldehyde will again come into primary alcohol. Similarly, in case of this also, ketone also, we can use the same reagent, that is lithium aluminum hydride or sodium borohydride. Okay, so if we use if we have ketone and if we use a strong reducing agent, that is a lithium aluminum hydride or sodium borohydride, then it will come back again to the secondary alcohol, right? Now we'll start with our conversions, right? So number one is butane 1-ol to butanoic acid. So butane 1-ol, so there are 4 carbon, right? So carbon number 1 has OH group. So butane-ol. So rest is hydrogen. So here comes H2, 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 H3. Now the product is butanoic acid. So you have to write the product, okay? Either in a rough side of your copy. So CH3, CH2, CH2, C double bond O, OH. Okay, so always you have to count the carbon right first. So here is 4 carbon, here is also 4 carbon. So no need to increase or decrease the number of carbon. So only thing is that you have to convert this OH into CHO group, right? So as I said earlier, so you have to do the strong oxidations. For that you have alkaline KMnO4, okay, or you can use as a acidic K2Cr2O7 for this oxidation. Okay, so in the next reaction I have written here, next conversion I have written here is a benzyl alcohol to 2-phenyl ethanoic acid. Okay, so benzyl alcohol, CH2OH. So this is our benzyl alcohol. Then we have 2-phenyl ethanoic acid. Okay, so ethanoic acid is the main group. So I'll write CHCOH. So this is our ethanoic acid. So it's a 2-phenyl. So this is carbon number 1, carbon number 2, 2-phenyl. So benzene as a branch is called phenyl. Otherwise, if it is a word root, then we use we name it as benzene only. Alright, so see, what happens here is that one carbon has been increased. So basically we can think of a step up reaction. Okay, for step up reaction we normally use KCN. Okay, so CN will displace the group here, but here is already OH is there, so OH cannot be displaced by CN. So you have to remove first Cl. So you have to first remove OH group. So for that we normally use this SOCl2, right? So if we use SOCl2, then OH will be replaced. This OH will be replaced by Cl. So this is CH2Cl. Fine. Now you can do is a KCl. So substitution reaction takes place. So Cl will be easily replaced by Cn. CH2Cn. Fine. Now if we do the oxidation, if we do the acidic hydration of cyanide, then directly it ends up with the COOH. So acidic hydration. So you can write as a H plus H2O, or you can write as a H3O positive. So this is acid catalyzed hydration. So when you acid catalyzed hydration of CN group, it will be end with the C double bond OH. So this is initially we have here single carbon, okay, along with this benzene ring. Now in the product we have one more carbon. So this CN, okay, the carbon from CN comes here, then this will be extra carbon in the product. The next conversion we'll do is 3-nitrobromobenzene to 3-nitrobenzoic acid. Okay, so we first will draw the structure. So 3-nitro. So benzene is the main word root. Okay, so benzene. So 3-nitrobromo. So if this is 1, 2, 3, 3-nitro, and 1 has to be bromine, right? So 3-nitrobromo-benzene. And our product is like we have to get this one, that is a benzoic acid. So it's 3-nitrobenzoic acid. So we know benzoic acid is benzene with COOH, COOH, and nitro group is as it is. So we just compare this starting reagent. So it's a nitro group is here. In product also there is nitro group. Now this bromine has been replaced. Okay, so it's very difficult to remove bromine from this benzene ring because it has some partial double bond character. Okay, and the bond is shorter, so it's very strong bond, we have already learned, right? So the best way is to remove this bromine is from making it as a Grignard reagent. So for that we need Mg and dry ether. Okay, so when we add Mg and dry ether, Mg gets inserted here, okay, between this benzene ring and bromine. So it will be Mg Br. Fine. So this is the Grignard reagent. Now when this Grignard reagent is treated with carbon dioxide, okay, in the form of dry ice, remember, dry ice, fine, solid CO2, then this product will be formed. C double bond O, OMZBr, okay, and nitro will be as it is. Fine. Okay. Now our problem is just to remove this magnesium Br. Okay. So this is simple. This is acid catalyzed hydration. Acid catalyzed hydration. That is H3O positive. So when you do it, okay. So actually come here, then OH will be come out. So plus we will have MgOH Br as a side product. So ultimately we raise that product. The next conversion I have written here is 4-methyl acetophenone to benzene 1,4-dicarboxylic acid. So first we'll draw the structure. So acetophenone, right? So phen 1. So acetophenone. First we'll draw this. Acetophenone. Aceto group is there and phenone. So yeah. So this is your aceto group phenone, right? So acetophenone. Then 4-methyl. So 1, 2, 3, 4. So we have CH3 here. Okay? 1, 2, 3, 4. So 4-methyl acetophenone. So from here we have to end with the product benzene with 1,4-dicarboxylic acid. So benzene with 1,4-dicarboxylic. So it's a C double bond OH. So here is also C double bond OH. So 1,4. Okay, I am choosing the one that's this side. So now we have to compare. First we have to do the carbon count, right? So carbon count is same. Here is one carbon with benzene ring, one carbon. Okay, so this has this has been removed here. Okay, so we know that if we do the strong oxidation, we have learned in the previous class also, like alkaline KMnO4. Okay, what will happen? That everything breaks in the first carbon. Okay, so okay, potassium salt of carboxylic acid. So here also we'll have a potassium salt of carboxylic acid. Okay, so if we use alkaline KMnO4, or you can use a acidic K2Cr2O7 also. Then you did this one, then you have to do acidification. Okay, so when you do the acidification, so this will come out and actually get inserted here in the both side. So ultimately we will reach to this product, that is benzene 1,4-dicarboxylic acid. Okay, the next conversion is butanol to butanoic acid. So we'll draw the structure butanol. So it's a 4-carbon compound, CH2, CH2, C double bond OH. So this is our butanol, right? And butanoic acid. So 4-carbon again. So OH. So here comes H2, H2, H3. So carbon count is same. So 4-carbon here, 4-carbon there. So no need to do further step of reaction. So simple thing is that you have to convert this aldehyde into carboxylic acid. It can be done in a single step, right? So as mentioned earlier, we have acidic K2Cr2O7. So it's strong oxidation. You do this strong oxidation, you will result in that carboxylic acid compound. The next reaction is bromobenzene to benzoic acid. So we'll draw the structure bromobenzene, Br, okay, and we'll write here benzoic acid. C double bond OH, right. So here, see, one carbon has been increased. Okay, so now we have already discussed this is very difficult to break the bond. Okay, so the main way out is formation of Grignard reagent. So we'll do with Mg dry ethyl. Okay, Mg dry ethyl. So Mg gets inserted here. So it will be MgBr, right? Now we need the carbon here. So as previous case, we do CO2, that is the dry ice. Then it will be C double bond O, yes, O MgBr, and it was like same as previous. So when you do acid catalyzed hydration, it will result in the formation of carboxylic acid.